Hi, welcome to a video lesson on finding the area under a curve. Imagine you have this curve and you want to find the area. You can do it by approximating the area using many rectangles. And that is what integration is all about. Great topic in integration. Let's get started. So let's just highlight that idea one more time. We want the area under this curve. We can insert a bunch of rectangles, find the area of those, and the sum of those rectangle areas is a good approximation for the area under the curve. However, there's these gaps here and these parts here which sticks up above the curve. So what can we do to solve that? We can have more rectangles. The more rectangles you have, you can see the smaller those little pieces that stick above and below are, and therefore more rectangles, better approximation of the area. And that is what integration actually does. It creates a infinite number of rectangles where it just becomes basically the area. Okay, so let's say we were looking to find the area under this function. This is a parabola, x squared plus 1, and we want to find the area from x equals 0 to x equals 2. So here's x equals 0, here's x equals 2, here is that parabola in red, that curve, and here we're trying to find this area underneath it. So we've created four rectangles, four pretty large rectangles to find the area. Notice these sit below the curve, therefore if we add the sum of these areas, we would have an area that's actually lower than the actual area under the curve because these sit below the curve. We could alternatively make the rectangles stick up above the curve. So these rectangles, if we added the sum of those, we would end up with an area that's higher than the actual area because they go above the curve. So somewhere in between is the actual area, right? This is too low, this is too high. All right, let's have a look at a table of value for those rectangles. If we have those four rectangles, so just like we have in the two diagrams, the lower sum, if we use the lower ones here, the sum of those rectangles is this area here. If we use the upper ones here, the sum of the area of those is 5.75. So you can see that this one is larger than this one. That makes sense again because these have all that excess above. So again, neither of these is the actual area of under the curve, but the actual area must be somewhere in between them because this one's too low and this one's too high. So what happens when we increase the number of rectangles? So here we're increasing the number of rectangles and then we get the new figure for the area of those rectangles. Notice what happens with the values as you increase the rectangles. Both of these values, which started off being quite different when we had four rectangles, are now quite similar. They converge on a single value. And that single value must be the actual area because as we add more rectangles, there's less and less of this excess, and therefore the rectangles are a much better approximation of the area. So we can see it converging on that area. Let's check it mathematically now. So before that, let's talk about what an indefinite integral is versus a definite one. Indefinite integral is what we've seen so far, something like this. We have the integral of a function in terms of dx here, or in respect to the x variable. Here is a function we can put in there. That's the function we were just looking at, x squared plus 1. So when we did indefinite integrals, we were able to integrate that and come up with a new function. And we already know those rules of integration. But the point is, when we have indefinite integrals, the result is always a function, a new function. Definite integrals look like this. Everything looks the same except for these two here. These two represent two numbers. They are called the bounds of integration. Basically a starting point and an ending point. So in our example, we've been talking about finding the area under this function from 0 to 2 on the x-axis. So that's what this integral will produce. That integral produces a number, and that number is this number. So again, definite integrals, once we have these numbers here, produce a value. And if you look at this 4 2/3, let's compare it. It's actually very close to what we found here when we had those 500 rectangles. So 4 2/3, that's basically this number right here. Okay, let's take a look at how we get that value. So now, so you know, to read that kind of definite integral, we say the integral from a to b of f with respect to x, where a and b are called the limits of integration. And we will use our GDC in this section. Oh, we'll do one without the calculator, but then most of it we'll be doing with the calculator. So let's take some notes on the page that has been provided to you. And on there we begin again looking for the area under this curve from x equals 0 to x equals 2, and we're going to use the definite integral. So here's our definite integral of that function from 0 to 2. With definite integrals, you do the same process. You do integration. We know how to integrate that. That becomes this function. But now since we have these boundaries or limits of integration, we put them right here. So we have these squared brackets, and these that were here are now here. And this process is pretty simple. All you have to do now is substitute that 2 into there. So notice x has been replaced with 2, and then subtract this function again with this value put into it. So this value goes in first, this one second, and you subtract the 2. If you do this mathematics here, you will get that value we just saw a moment ago, 4 and 2/3. So that tells us the exact area under this curve from 0 to 2, and it matches what we saw when we had all those rectangles. Okay, so here's what we had from rectangles, right? That figure, very similar to that. All right, this can be done on our calculator. Let's take a look how. The calculator, here's how it's done. We're going to press the math button right here. And number 9 on this list, you can scroll up to get to 9 rather than down. So there's number 9 right there. Function integral right there, enter. And look, we have a definite integral we can enter. And our integral was x values from 0 to 2. And then you put the function in. The function was x squared plus 1, I believe it was. Whoops, that's not plus. And then at the end you have to put in relation to x. That's our variable in this function. Press enter. Let's see what it gives us. There it is, 4 and 2/3, same answer. Great. So our calculator does this for us. We'll be using this a lot in our lesson here. Excellent. So let's take a look at this one on your page. It says find the area geometrically. Well, geometrically means let's not worry about integrals for a moment. This is just a simple shape. If we want to find that area, it's a triangle. So we can use area equals base times height divided by 2. And we can see this base, it goes from -2 to 6. So the base must be 8 in length, and the height must be 4 here. We can see it goes up to 4. So 8 times 4 divided by 2, 16. That is the area of this triangle. Let's see if integration gives us the same thing. So we're going to set up the integral. We know that this curve, well, it's a line in this case, but it's still called a curve. So that function is half x plus 1. We set up an integral, definite integral, from -2 to 6, -2 to 6, and we run that integral. All right, so the integral is 1/4 x squared plus x. Okay, double check, you know how to integrate. And here's our bounds of integration, -2 to 6. So again, we put the 6 in that function minus that -2 we put in that function. And when you do all that work, if you work through it, you will be able to confirm it gives us 16, just like we saw here. So geometrically, it's a triangle, easy area. Integration gives us the same area. Fantastic! You've learned a wonderfully powerful tool in mathematics. I hope you're excited about this. It's really great. Okay, try these ones here. What's this area here? Find it geometrically. So just look at the shape and find the area. Well, that's just a rectangle. And, let's look up here first. Okay, so area of a rectangle is just base times height. 4 times 3, we have 12. Using our calculator, we could set up this integral. If you don't have your calculator, still write this on your page. There's our integral, -1 to 3. And the function is just 3, right? It's just y equals 3, a horizontal line. So function is 3. And punching that in our calculator, using the technique I showed you, confirms we have 12. This one, we have a quarter of a circle. We know the area of a circle. It's pi r squared. And we have a quarter of it, so divided by 4. And we know the radius of the circle is 3. We can see it here. So pi 3 squared divided by 4 gives us this value here. Using our calculator, the integral would be set up like this. We can see the function is given for this semicircle. The function looks like this, and we can go from 0 to 3. Run that integral, guess what? It will confirm the same area. This is incredible. Math works. It's fantastic. Last one, it's a trapezoid. You might not know that area formula, but it is this, base 1 plus base 2 times height. So base 1 is like one of these parallel sides. So this is called a base, and it's called a base. Those are parallel. Add those two, multiply by h, which is your height right here from base to base. The height is 6, and then divide by 2. That gives us 18. Using the calculator, once again, we run an integral, definite integral from 0 to 6. There's our function, because it's that line, it gives it to us. And run that integral, guess what? 18 is our answer. That is fantastic how it works like that. I love it. Okay, try this one here. Okay, so you've tried it. We set up a definite integral from -3 to 3. Our function is this one here. That's an absolute value function, which has this V shape like this. We can run that integral in our calculator, 9. And then looking at it as a triangle, half times base times height, also 9. Amazing. Love it. It's so fantastic how it works. And now let's look at something interesting that occurs. We have this line here. Notice the line is above the x-axis and below the x-axis as well. We want to know the area from -3 to 2, so that full area here. All right, geometrically, we have two triangles, right? So area 1, this triangle has an area of 4, and area 2, this triangle has an area of 9. We know the base is 3, height is 6. We can do that 3 times 6 divided by 2. Anyway, so by using the definite integral, let's see what happens. Oh, the total, by the way, that's 13. So we know that total blue area is 13. Using the definite integral, however, if we set up from -3 to 2, for that function, we know it's this line, 2x plus 2, and we run that definite integral, it gives us an answer of 5. You can double check if you have your calculator, but it is 5. It doesn't match this 13. So does that mean everything we've just learned makes no sense and everything's broken? Not exactly. Let's see what happens. Let's think of this as two zones. Rather than one integral from -3 to 2, we're going to do one integral from -3 to -1, which is here. So we're just going to look at this area, and then we can do another integral for that. If you find this integral, you will get an answer of -4. So it actually gives this area under the axis as a negative area. And now if we try the other piece, so we've just done that one. Now if we go from -1 to 2, run that integral, that gives us an area or a value of 9. So notice now that those two combined will give 5. So that is an important idea about integration and area. When we have an area below the x-axis, it's considered negative area, and here positive. So the integral here gives that value there. Very important to know that. Okay, the solution to that problem, if you want the actual area and not have this negative thing factored in, is to do an absolute value of the function. Notice the absolute value is there, because that's what absolute value does. It changes negative values to positive values. So this is basically saying any negative y values become positive. So it's like a reflection over the x-axis. So what that does is take this portion here, reflects it over the axis, and finds this area instead. So if you put this integral in your calculator with the absolute value, it will give you that answer of 13, because it's going to do this positive one and this positive one and give you that answer. That's very important to know. In your formula booklet, this is what this hint says. In your formula booklet, you will see this area function with the integral given like that with the absolute value. Okay, take pause and just read this. Make sure you see what's going on here. It kind of recaps the things we've been talking about. But the thing you should know is that when we are running integrals of functions, we don't worry about that negative bit. We don't have to do that absolute value. That's only if you want the actual area. But if you want a theoretical or like an abstract area, we just run the integral as it is. So let's look at this one. This shape here, we have all these 4 components. We want to find that full area. We're going to do it geometrically to begin. So that first green triangle, 2 times 4 divided by 2 has an area of 4. The next triangle, this orange one here, is also an area of 4 if you do base times height divided by 2. Next blue one here, base times height divided by 2. And this time I called it negative because we're sticking with what the integral does. If it's below, it's negative. And then that last rectangle here, 2 by 4, 8. So that total area is 14. That's including that negative bit here. Now, how would you do that on your calculator or running an integral? Well, here's the 3 functions for those lines. Okay, we're given these 3 lines here. And then we can confirm. So we're going to run one from 0 to 3 because we have that whole line there. It doesn't change. So we're going to run one integral from 0 to 3 because that'll give us the area of the green and half of this blue one, making this negative as well. That answer is 3. And then we're going to run one from 3 to 6, because now we have this line here from 3 to 6, and that will give us this negative portion plus this positive portion, and that integral is 3. And finally, we're going to run the last integral from 6 to 8, and that gives us 8, and that matches the area of the rectangle because that is just that rectangle there, right? Add those up, 3 plus 3 plus 8, and we get our answer of 14. And captured within these two again is that little negative portion of that triangle. A little bit of it here and a little bit of it there. Pause if you need to. This is a very important slide in terms of all these ideas coming together. And please try one last question. Try this one here. Find the area of this one. Again, sticking to the definition of integral where this will be counted as a negative area. See if you can figure that out. Okay, that was tough. You had to make equations, but it all works out here. Here's the equations to the lines. Here's the area. Here's the final figure. Check your work carefully. It actually ends up being 0. Interesting. And I think we'll end this video there. So study this carefully. There's another video coming up.